Good evening, everyone. Welcome to this Foundation Engineering uh, class. Today is week 12, and it is the last week of this course. And after that, you will have exam on this. And one thing that I will also take one extra class of for this foundation engineering course tomorrow at same timing. So let's start our today's session. So first of all, I introduce myself. Mm, So my name is Rajat Bani. I am a PMRF research scholar at IIT Assam Dhanbad, and I am a TA of this foundation engineering course under Professor Dilip Kumar Vaidya sir. And I have also 6 month teaching experience in Nptel as a TA, and my previous course was ground improvement, and which also conducted by Professor Dilip Kumar Vaidya sir. So today we are in week 12. It is our last week in regarding this foundation engineering course, and after that you will have exam on this course, so be prepared for exam, and whatever I am discussing till now, please go through once and try to solve as many as problem by yourself regarding this course. And I'm also sharing the previous year assignment problem with solution. So try to solve it also, and also try to solve this year question also, this year assignment question also, which is very important for your marking system, because it is these assignments, this year assignments also are included in your 40% weightage. Take 40% weightage to your marking system. So before starting our discussion, I made one or two things here to make one or two things here, that this session is recorded and it will be uploaded my YouTube channel, and whatever I am discussing here, it will be shared to you and share to everyone to my Google Drive. And if any discrepancy happen, that means network issue or any other things happens, the disturbance in audio or video, so don't worry. It will. I will try to solve it and rejoin the meeting again. So in our meeting, I will also give 5 minute breaks. So let's start our session now. So in week in just before discussing the week 12, in previous week, that is week 11, we just start the dynamics of foundation and detail about the machine foundation. So today, this week 11 class is regarding the same of this dynamic foundation, and in this class we try to solve some numerical problems regarding this dynamics of foundation theories. So before start, we just briefly discuss the previous week lectures very quickly. After that, we try to solve few problems and conclude our session. So let's start our session. I am sharing my hello. Uh, I am sharing my screen. So please be patient. I think it is visible to everyone. My slides are visible. So let's start with the uh, previous week's lectures discussion of the foundation engineering. So dynamics of foundation. So in previous week we discussed the what difference between the static problem and dynamic problem. And in static problem, we just use the flow force equilibrium. Uh, uh, just there is no inertia force we use, but in dynamics problem, uh, where we applied force is time dependent, and and also there is a inertia force coming picture. Then we study the different types of force, that is periodic force, random force, and transient force. And based on these different graphs also we plotted. And you see that in periodic force there is a repetition after a certain period of time. So we can say that this is a periodic in nature. Then random force we cannot define properly. It is just random. And transient force is that force, dynamic force, which is reduced or vanish after a certain period of time, before a certain period of time, and before it is vanished, it gives a certain amount of vibration. And this will happen due to the presence of damping in our system. Then there we studied the source of dynamic load like operation machines, vehicle movement, pile driving, blasting operation, wave motion, earthquake like that. After that, we study or differentiate the different types of vibration. There is two types of vibration mainly, free vibration and forced vibration. Free vibration are that type of vibration which is vibrate without any help of any external force. But in nature, there is nothing called free vibration, because we to produce the free vibration there is we need some little amount of external force. After that, we remove this external force, and we if the system is remaining that type of vibration, we can call it a free vibration. And then for vibration, so by name itself it is for we apply some external force, so it is called force vibration. So in free vibration, force vibration, again it is differentiated in two types, which is called undamped system and damped system. Undamped system, that means the force is continuously going on without any dissipation of energy. In damped system, the force is after certain period of time, the force is vanished due to the dissipation of energy, and it is occur because of the nature of the material property. So we for these different types of vibration, we create or we uh, produce different mathematical equation. So and this vibration system we mostly difference mostly uh, idealized as a mass spring disperse system. So a certain mass is there, which white mass is m, and this mass is attached to spring, which coefficient is k, and attached with some disperse, which coefficient is c. So mass spring disperse system very easily we can define uh, um, or very easily we understand this vibration system. So you see that here it is shown different types of vibration system. So we already told that in undamped system the force or vibration is continuously go on with if there is no external arrangement, if we not apply, then in damped system this after certain period of time the force is vanished. So we now if we represent these different types of vibration system by mathematical equation. So you see that the free vibration, free undamped vibration, free vibration, uh, free undamped vibration. The mathematical equation is mu double dot plus ku is equal to 0. So this free undamped vibration, the if we solve this equation with the help of mathematical tool, so our displacement for this system is equal to u small u is equal to capital U into cos omega t plus alpha. And you know the one thing that you remember one thing that for natural period or for natural frequency, we to find out the natural frequency or natural system or natural property of the system, we always use the free undamped vibration equation. And here the omega is represented the natural uh, frequency or natural radial frequency or angular frequency. Then there is a free vibration damped system, and in by the equation free vibration damped system, we identify the critical damping, under damping, over damping. So by solving the equation, there is thit- a situation is happening, and if our C by C means coefficient of uh, damping divided by 2x of m, and one time is k by m, which is nothing but the natural frequency omega m over k by m. If c by twice m is greater than k by m, it is called our damped system. If c by twice m is equal to k by m, it is called critical damping. If c by twice m is less than k root over k by m, it is called under damping. And based on this, we find out the critical damping ratio, which is equal to 2 root over k by m. And by this we can again find out another term which is called damping ratio, which is nothing but the coefficient of damping divided by critical damping. So this free vibration undamped system is very important to identify the different damping properties of the of a material. Then we study in next lecture we study the force vibration and the undamped system. So force vibration undamped system, we actually it is similar to the free vibration undamped system, but here is one thing that we use external force to conduct or produce this type of vibration, and this external force is a time dependent force. If you in force vibration, you remember that this equation is equal to 0 because there is no force applied in free vibration, sorry. So but in force vibration, this equation is equal to ft. So after solving this equation, we find out the displacement is equal to the f naught, which is the, if we represent this ft is equal to f naught sine or cos omega t, then we find out that displacement is equal to the uh, f naught by k divided by 1 minus omega by omega n whole square into sine omega t. And for maximum or for amplitude of this displacement, if you remove this term, we get the amplitude of this displacement. And in this amplitude is depend on the magnification factor, and this magnification here it is 1 by omega minus omega n whole square, where omega is the force uh, angular frequency of the force uh, or system, omega in the natural frequency. So if you frequency, so if you plot this And this omega by omega band we also call frequency ratio. And if you plot this magnification factor with the amplitude, we get magnification factor with this. If you plot magnitude factor, this magnitude factor with the frequency ratio, then we get this type of plot. So by this and this type plot is for undamped forcing vibration. And by this plot, by seeing this plot, we say that at frequency ratio 1, that means omega when omega is equal to omega n, the curve is approached to the infinity. Either it is negative direction or it is positive direction. And this is happened due to the or phenomena resonance. And we know that in resonance, if the forcing frequency matching with the natural frequency, then the amplitude of the system is suddenly get very huge. And due to this, there is a destruction of the system due to this occurrence of the resonance. So it is very critical for designer to identify the resonance frequency of the system, because if you design if you don't avoid this resonance, then there may be in operation there may be on time when the frequency matches the resonant frequency, and this may cause the damage of the foundation system. So for designing purpose, we should always avoid this type of situation. So for this, when we for this we have to design uh, either in a way that our question frequency either much more greater than one or either much more less than one. So to avoid the resonance, then there is a representation of the rotating mass system in a foundation system. So due to this rotating mass, there is a occurrence of the vibration, and we see that if Mars is rotate uh, in a machine, it produces a force which is equal to the me omega square, where m is the rotating mass. M is the rotating mass, E is the radius at which it is rotates, and omega is the generated frequency or angular frequency due to the rotation. So by this rotating mass, we produce the different type of vibration like vertical vibration, torsional vibration, rocking vibration. So you see that the vertical vibration, if we arrange this type and if you maintain this type of arrangement, then we can see say that this vibration is vertical direction. If you arrange if this way, then it is called torsional vibration, because this system is rotated in this direction, this system is rotated in this direction. So it is create a torsion. And due to this arrangement, it is vibrate downward this side, it vibrate down upward this side. So it is called a rocking vibration, rocking type nature of vibration. Then in this figure we show the different types of vibration. So if the body is vibrating in vertical direction, then it's a vertical vibration. If the body is vibrating in longitudinal direction, it is called longitudinal vibration. If body is vibrating in horizontal direction, it is called horizontal vibration. If the body is vibrate with respect to the vertical direction, it is called torsional vibration. If his body is rotate or vibrate in with respect to horizontal direction, it is called rocking vibration. Again, or pitching vibration. If your body rotate in a longitudinal direction, it is called rocking vibration. Uh, so these are the different types of vibration. In a 3D body, there are only six type of vibration: vertical, horizontal, longitudinal. Then these vibrations depends on the axial deformation of the body, and then rocking, torsional, and pitching vibration, which is depend on the rotational deformation of the body. and these are the different mathematical equation of this type of vibration, and this is for undamped force vibration. So for vertical vibration, we use mass, and but vertical and horizontal vibration. But in rocking and torsion vibration, we use the mass moment of inertia instead of mass. And for this we use moment torsion, and for this we use axial force, which is also dependent on the time. Then there is a different we studied in previous class. The for different types of vibration there is a different types of stiffness, and this stiffness is calculated for a circular footing which dimension or radius is r, and the soil properties are g, shear modulus, and Poisson's ratio, which is dependent on the soil properties. So by these formulas we easily find out the different stiffness for different types of vibration, which is help to solve this mathematical equation. You see, then now we come to the force damped vibration. So in force damped vibration, one extra term is added, which is C into U dot, which is nothing but the damping term, dashboard term. So, but in force vibration, we use two types of force: external force. One is constant force amplitude, another one is rotating mass system frequency dependent force amplitude. And in frequency dependent force amplitude, the this amplitude is continuously changing because we use omega. We use the term which is equal to me omega square sine omega t, and constant we use f naught sine omega t. Now, after solving for constant force vibration, how we get the displacement is equal to the amplitude is equal to the f naught by k uh, divided by whole divided by 1 minus omega by omega square whole square, omega square by omega square whole square plus 2d omega by omega whole square whole to the power half. So this 1 by this term, 1 by this term is nothing but the magnitude magnification factor. So if we plot again this magnification factor with the versus this frequency ratio, we get for constant force term force system we get this type of plot. So you see that for constant force term, the at a lower frequency ratio, the force is started this vibration is started with from 1, but after when the potential issue is equal to 1, then there is a sudden increment of this vibration amplitude in the vibration amplitude, and it is mostly dependent on the damping. If the damping ratio is less, then this amplitude is more. And so if material term, if we say that the damping is infinity, or sorry, 0, then this amplitude will become infinity. And so by this way we call that it is nothing but the resonant happen in this. So after the frequency ratio, that means if one, that means if the frequency ratio greater than one, the this amplitude try to reduce, and it is become this magnitude factor become less than one. So we have to design our system either in this part or in this part. We don't use this middle pass of our design. So we have to design in such a way our amplitude should lie either in this type of position or lie in this position, which makes sure the safe system of this uh, foundation. Then there is a rotating mass system. So in rotating mass system, we replace this F naught by K by this term me by E by M into omega by omega n whole square. So where M is the rotating mass, M is the total mass of the foundation. So if you plot this and this 1 by, so if you neglect or this term, or you put this term is here, then this entire term is called magnitude factor. And if you plot this magnitude factor versus frequency ratio plot, then we get this type of graph for rotating mass. And we see that it is a little bit opposite to the constant force mass system, where the constant force mass system start with 1 but in the lower frequency ratio, but it is in lower frequency ratio it will become less than 1, and at a higher frequency ratio it approach to the 1. But at frequency ratio, in both the case, at the frequency ratio is equal to or almost equal to 1, it get the highest amplitude, uh, because same thing resonance happen in this system. So we try to design either this way, in this position, or in this position. Do not use this position in our design. So that's it of this previous class. So again, there is uh, for different types of vibration, different equation are there for damping system, and it is summarized. This lecture is summarized. Whatever we're discussing is summarized here. So you see that one thing is that here, that the resonance frequency for constant force mass is omega. You say omega d is equal to omega n root over 1 minus d square. But for rotating mass system, omega d is equal to the omega n divided by 1 minus d square. Or omega n is the natural frequency, which is equal to the root over k by m, and d is the damping ratio, which is equal to c by cc. C is the critical damping ratio of the coefficient, and c is the damping coefficient of that at present system. And there is, if we again simplify these two terms, these two amplitude, then this resonant amplitude become f naught by if if the this damping ratio is frequency ratio omega by omega n is 1. That means if fn omega by omega n, or at a resonant frequency, we this amplitude is become like this way. That means f naught by k into 1 minus 2d by root over d square. Again, if you simplify, f naught by k in divided by 2d, because the damping is ratio is very small, we neglect this part. Again, it is become me by e, me into e divided by m into 1 by 2d for simplicity. And this amplitude is called nothing but resonant amplitude. And it is why? It is because uh, this will get at the resonant frequency. That means when the frequency ratio is equal to 1. That means omega by omega n is equal to 1. Now we try to solve in, now we start our today's. So then we study the different guidelines to design for designing purpose. So we should maintain our amplitude. Natural frequency should be lie in this range. We will go through it. We're not discussing here again. So now we start the today's lecture, today's session, and this lecture is mostly belongs to the numerical problem. So we try to solve one by one these problems. So it is very simple problem. So we now try to solve, and this for solving this equation. Sorry, for solving this numerical, we need the concept of the previous class. So which I quickly discuss now. So let's start solving this question. So the first question of this today's session is that it means lecture number 56 of this 12 week 12, and that an unknown weight, it is W, is attached to an end of an unknown spring K, and the natural frequency of the system found uh, to be 90 CPM. That means cycle per minute. If 1 kg is added to W, the natural frequency reduced to 75 CPM. So determine the unknown weight W and spring constant K. So first, to solve this question, we need to find first omega of this system. Natural frequency, natural radial frequency or angular frequency of the system. We know that it is root over K by M. So for our case, both K and M is unknown, but conditions are given that F, for first case, F is equal to 90 CPM per minute. But for this equation, we need F in cycle per seconds. So we divide this 90 by 60 and get our frequency in cycle per second, which is equal to 1.5 CPM, CPS, and it is also called hertz. Then it is F1, first case. And second case, when we add a extra 1 kg, then F2 become 75 CPM. If you divide it by 60, it is give 75 divided by 60, which is equal to 1.25 hertz. Then we know that uh, omega n is equal to 2 pi f. So first case, omega n1 is equal to 2 pi f1, which is equal to, we multiply by 1.5 into 2 into 1.34, that is value of 5, which is equal to 9.42. Then omega n2 for second case is equal to 2 pi f2, which is equal to 1.25 into 2 into 1.34, equal to 7.85. It is 9. Now we use this relation where omega n square, I'm round it there due to the limited space. Uh, then we use this equation. Omega n square is equal to the root over k by n. Or if you write again k into g divided by w. We know that m is equal to w by g. So we read right with k root over w. G is, the value of g is 9.81. So we further simplify. So if you square both sides, then we get omega n square is equal to k 9.81 k by w. Then in our equation we get omega n1 is 9.42. So put for first case, uh, omega n square is 9.42 square is equal to 9.81 81 k 1, sorry, k, both the case k same divided by w. And second case is omega n square is 7.85 whole square is equal to 9.81 into K divided by W plus 1 kg mass divided by 9.81 because the mass, sorry, into plus 9.81 because 1 kg is 9.81 Newton weight plus 9.81. So solve two equation, you get the answer. So I will wrap this part. So if we put K here, or we simplify that, K is equal to, for first equation, K is equal to, this is equation 1, equation 2. So first equation, K is equal to 9.42 square divided by 9.81, 9.05 omega n, so W is equal to K. Then if you put this in second equation, which is equal to 7.85 whole square is equal to 9.81 into this 9.04 W divided by W plus 9.81. So solve it and get the W, which is equal to 7.85 square uh, divided by 9.81 divided by 9.05 404 and minus answer divided by 9.81 divided by answer. So our W we get 32.15 Newton. If we put this here into this equation, this we get our K into 32, sorry, into 9.04, which get our K is 90.64 Newton per meter. So, so it is, this is very simple problem. So we get our W is, this unknown W is 32.15 Newton, and unknown K spring constant is 290.64 Newton per meter. I think it is understand to everyone. Now move on to question number, second question. That is, it is said that a spring and dashboard are attached to a body which weight is 140 Newton, and spring constant is given 3 kilonewton per meter. Dashboard resistance force is given 0.75 Newton and the velocity is given 0.06 meter per second. Determine the following of our free vibration, whether the system is overdamp, underdamp or critical damp. So we have to find out whether by this given data we have to identify whether the system is overdamped system, underdamped system or critical damp system. So first we find out the mass. So mass m is equal to 4 W by G. So which is 140 divided by 9.81, 140 divided by 9.81, which is equal to 14.27 kg, I think. Then spring constant is given K is equal to 3 kilonewton per meter. So we have to convert it Newton per meter, which is equal to 3000 Newton per meter. Then we have to find out the damping coefficient for this system. By this given arrangement, we know that damping coefficient is equal to damping force by velocity v. Damping resistance or force is given 0.75 Newton. Velocity is given 0.06 meter per second. So it is become 0.075 divided by 0.06, 12.5. Now we know that if this C by twice m is there is one term C by twice m, there is one term root over K by m. If it is greater than, then it is over damped. If it is equal to, then it is critical damping. If it is less than, then it is under damping. So we have to find the first C by twice m. So C here 12.5, m is 2 times of 14.27. So it is divided by 2 times of 14.27. It is become 0.43, this ratio. Then root over K by m, which is called natural angular frequency, which is equal to 3000 divided by 14.27 root over, and then root over 3000 divided by 14.27, which is equal to the 14.5. So we see that this ratio K by m is greater than this ratio C by twice m. So, or we can see that C by twice m is less than the ratio root over K by m. So we call this system is a underdamped system. So our answer is this system is underdamped. So it is very simple. So I think it is understand to everyone. So we move on to next question. So in next question, it is related to the rotating mass concept. So it is said that a counter rotating eccentric mass exciter is used to produce force oscillation uh, of a spring supported mass. By varying the speed of rotation, a resonant amplitude of 5 mm was recorded. When the speed of rotation was increased considerably beyond the resonant frequency, the amplitude appeared to approach at constant value of 0.6 mm. Determine the damping factor of the system. So for this we use this one concept, forced damped vibration for rotating mass system. So if you remember, we discussed in previous class, also in our today's class, that in rotating mass, forced of damped vibration system, the amplitude we find out is this. And if you remember, at this U by ME E by M for resonant frequency, it is become 1 by twice d root over 1 minus d square. And if you approximately, it is 2d. So if this ratio is getting 1, if this frequency ratio is approached to less is greater than 1, it means at higher frequency ratio we get this ratio is equal to 1. So in our question, uh, it is said that at a resonant frequency which is equal to U divided by ME E by M, which is also equal to twice T, our amplitude is equal to 5 mm. Actually, this actual equation is 1 minus 1 divided by 2d into root over 1 minus d square. But for this, we know that damping coefficient is ratio is very small, so we neglect this term. And this u is in this case is 5 mm. At then there is when there is a constant value is achieved, which is zero point 0.6 mm, we said that this ratio is become 1. And at this case, this u is zero point 0.6 mm. So for this case, we find out the ME by M value, which is nothing but equal to zero point 0.6 mm. If we put this here, we get the value of D. So if you putting this value here, F 5 by zero point 0.6 equal to 1 by twice D. So get the D is equal to zero point 0.6 divided by 5 divided by 2, which is equal to D is equal to zero point 0.06. If you represent in percentage, which is become 6%. So our answer is 6%. Our damping ratio is 6%. It is very simple problem. So I think it is understand to everyone. So now moving to the next question. See, we use this concept here. So now moving to the next question, which is little bit this similar type, uh, but here we use a constant force system. So I think this is also same. Uh, Sorry, no, we don't use here constant force. Same concept we use here also, but this is for the constant force system. So we see that for constant force system at a lesser frequency ratio, its value is approaching towards this ratio is approaching towards 1. So first we dictate this question first. A single degree of freedom system is excited by a sinusoidal force at a resonance. The amplitude displacement was measured by to be 2 mm at an exciting frequency of the 1/10 of the natural frequency of the system. The displacement amplitude was measured to be zero point 0.2 mm. Estimate the damping ratio of the system. So it is similar. So we know that this frequency ratio U sorry, amplitude ratio is equal to root over 1 by 2 t root over 1 minus t square. So for simplicity, we neglect this term. So this remain is equal to 1 minus 1 by 2d at resonant frequency. So again at resonant frequency, u is equal to 2 mm. Then at 1/10 of the natural frequency system, 1/10 of the natural frequency system, they say omega by omega n ratio is equal to 1/10. So, or we say that at when the frequency ratio is less than 1, this u by, for simplicity, u by f naught is approaching towards 1. And at this situation, our amplitude is 0.2 mm. So for this equation, you get the f naught by k, and if you put here again in this equation, you get the damping ratio, which is 1 by 2t is equal to 2 by zero point 0.2. So our answer is zero point 0.2 divided by 2 divided by 0.05, which is, we can say, 5%. So by this simplest way, we find out this answer. Or you do one thing, that we just we just put this value in this equation, omega by omega n whole square plus 2t omega by omega n whole square. So from this equation you get one equation, from this equation you get one equation. Solve this and find out. If you put the omega by omega n is 1 by 10, then it is understand to everyone. Or either for simplicity we use this equation. So we know that at when the frequency ratio is very less, this u by f naught by k is pushing towards 1. So for simplicity, we use this ratio is equal to 1, and put this value u, find out the f naught by k value, put this f naught by k value here. We get, we also know the u value here. And for again for simplicity, we remove this term, and we easily find out the value of damping ratio. So I think it is understand to everyone. Then, and for this we use this equation mostly. We can use or use just this simpler form. Now we move on to the question number, next question. So I think this is the last question of this lecture, number 56. So it is said that a body weighing 600 Newton is suspended from a spring, which deflects is 12 mm under the load. It is subjected to a damping effect adjusted to a value of zero point 0.2 times that requires for critical damping. Finding the natural frequency of the undamped and damped vibration, and in latter case determine the ratio of the successive amplitude. So first we find out the mass of the system, which is m is equal to W by G, which is 600 divided by 9.81, which is equal to divided by 9.81, which is equal to 61.16 kg. Then we find out the spring stiffness K, which is equal to W. Here it is force applied W and by delta. Delta is here 12 mm. So W is 600. Delta is 12 mm. So convert it in millimeter. So which is equal to 600 divided by 10 to the power minus 3 divided by 12. 600 divided by 12 into 1000, which is equal to 50,000 Newton per meter. Then we have to find out the damping ratio. So we know that damping ratio is C by C. C. So here C given 0.2 times of CC critical damping. So it is become zero point 0.2 or we can say 20%. Damping ratio is 20%. Then we have to find out the natural frequency. So we know the natural frequency omega n is equal to root over k by m, where k is here 50,000, m is given 61.16. So root over 50,000 divided by 61.16 becomes 28 point. I write here omega n is equal to 28.59. Now find out the damped vibration, and this is undamped vibration. Natural frequency for undamped vibration, natural frequency for damped vibration, which is called omega d, which is equal to omega n into root over 1 minus d square. So put value, all these value, omega n we find out 28.59, d is value of d is zero point 0.2 and it is whole square. So it is into root over 1 minus 0.2 whole square, which is equal to 28.01, and the unit is radian per second. Here also radian per second. So remember. Then you have to determine the ratio of the successive amplitude. So ratio of the successive amplitude, we know that uh, so So I think this concept is not uh, completed here. In the upcoming lectures, we can complete it. So for solving the question, we use one term which is called logarithmic decrement. So in logarithmic decrement, we have to find out the damping ratio. So it is said that the logarithmic decrement delta is given is a logarithmic of the ratio of the successive amplitude, which is we can say u1 by u2, which is further equal to 2 pi into d. So you see that this. So we have to find out this successive ratio of the successive amplitude. So the ratio of the successive amplitude, if you equate this term, it just become u1 by u2, which is equal to the e to the power pi 2 pi into d. And put this value e to the power 2 pi into zero point 0.2. So we get this ratio of 2 into 1.4 into 3.14 into zero point 0.2, which is become 3.51. So our answer is for determine the ratio of the successive amplitude. Uh, the answer is 3.51. So for this we use logarithmic decrement. So where delta is 2 pi d is equal to ln u1 by u2. So if you equate this only, which is equal to e to the power 2 pi d is equal to u1 by u2. We have to find out this in our question. So we put using this equation. So put value of d, which is equal to point 0.2. So which is after that we get the ratio is 3.51. So I think we completed the lecture number 56, all this problem. So before starting with the upcoming lectures, we now take 5 minutes break. After that, we will again join and discuss our further lectures. So please stay on the line. Hello, friend. Welcome to this session again. So we move on to the next lecture, which is lecture number 57. So, in lecture number 57, we will discuss this theory again. We differentiate these theories, which is one for constant force system, one for rotating mass system. So, in constant force system, we use F naught by K, where F naught is the constant force system amplitude, K is the spring constant, or ME, e- uh, ME, round, ME omega square is the rotating mass force amplitude for this rotating mass system, and m is the total mass of the system. And for maximum amplitude, we use this equation, which is we get at resonant frequency for uh, resonant frequency for both the cases. This equation is looks similar, but the main difference is this term. So you should remember this. Now there is a machine arrangement of the machine foundation. So for this we get, and this is find out for IS 5249, I think, and year 1990 1999. Then by this arrangement we get actually this is a test where we find out the stiffness of the system K, and before stiffness of the system we find out the stiffness of the system, we use U is equal to we use one term, that is coefficient of elastic uniform uh, compression, and this coefficient of elastic compression we actually find out by this test, where we use one similar type of setup for the machine foundation, where we use some CC block concrete blocks. Then we measure the here we use one machine, and for measuring the vibration we use some pickups in meters at a distance d1, a distance d2, and this foundation is constructed at a depth of d, and this dimension of this foundation is 1 meter by 1 meter. So by this arrangement we get one plot, which is amplitude versus frequency curve. So why we need to find out compression, elastic compression, elastic uniform compression in coefficient, why we need, because of find out the K, and this K is important to solve this dynamic equation. We know that for forced damped vibration, equation is mu double dot plus cu dot plus K into U. So M is, you know, the foundation mass, C is the damping of coefficient of the system, and this we can get by just material properties, or sometimes it is by we directly get in some test. And K we have to find out, and for K we use some basic equation, which is for vertical it is 4gr by 1 minus u. But it is a theoretical concept. We get it a practical way. So for practical, we have to find out first this coefficient of elastic uniform compression, and after finding this coefficient elastic compression, if you multiply with the area of this foundation, which is for test it is 1 meter by 1 meter, then we get the spring coefficient. It is K. So we see that there is a one equation or formula is given to find out this coefficient of uniform compression. So how this equation arrive? You see, we know that omega is equal to 2 pi f. If you and again we know that omega is equal to root over k by m, and if you square it, it will become k by m is equal to 4 pi square f square. And we know that then k is equal to 4 pi f square into m. We know that cu is equal to k by a. Then if you put this k value here, 4 pi f square, sorry, pi square f m square into m divided by a, we get the coefficient of uniform compression. And this coefficient of uniform compression, and to find out this coefficient of uniform compression, we need to find out the frequency. And we find out this frequency, the frequency by after measuring the amplitude percent frequency curve in CPS, that is cycle per second, and at the maximum amplitude we get the this frequency. The we have to identify that frequency which will give the maximum amplitude, and these are our targeting frequency. And if you put this frequency value here, and in this formula we get the coefficient of uniform compression, and this is for test foundation 1 meter by 1 meter. But it is if we use this for different types of foundation size, because in real life the foundation may be bigger than the 1 meter by 1 meter. So we modified this equation by a coefficient root over a by f, where a is our test foundation 1 meter by 1 meter, and cu is the our uh, test coefficient of compression index. F AF is the real field foundation size, which sometimes it is 5 meter by 5 meter or 10 meter by 10 meter. So all these value if we put, we get the original coefficient of compression index for real foundation. Then we use half bandwidth method. This equation is called half bandwidth method. By this half bandwidth method, we easily find out the damping ratio. So we see that you can see that the amplitude of the system versus frequency curve is like that. It is first going upward, then it is reducing downward, and this is happened due to the resonance. And this frequency is called Fn. So to find out the damping ratio, we need to average this frequency. For this, we use the amplitude, uh, which is equal to the uh, 1 by root 2 times of the maximum amplitude. And at this amplitude, we get two frequency. One is called F2, another is called F1. So by this equation, D is equal to F2 minus F1 divided by 2Fn. Fn is nothing but the natural frequency, or we can say resonating frequency, where we get the maximum amplitude. So put all this value in this equation. If we put, we get the damping ratio of this system. And to find out the F2 and F1, we need the value of the maximum amplitude, and at 1 by root 2 times of the maximum amplitude, we get the two frequencies, One is called F1, another one is called F2. From 2, which is greater, we put it first. We say F2 is greater than F1, then we use this equation D is equal to F2 minus F1 divided by 2 Fn. Now we come another concept which is called logarithmic decrement concept. By this logarithmic decrement concept, we have to find out the damping ratio of the system, and this concept is based on the two successive ratio of the two successive amplitude. And if you remember in our today's class, last question of this lecture number 56, we use this equation. We say that told that this concept is not covered yet. So here is the concept. We see that uh, this logarithmic decrement is represented by delta, which is equal to the log of the natural log of the ratio of two successive amplitude. And if you put this amplitude value here, this equation is look like 2 pi d divided by 1 minus d square, which is almost equal to 2 pi d. If you, because we know that d value is much more less than 1, so we write is and 2 pi d. But it is for one successive frequency ratio, amplitude ratio. But if you get, but if you need to find out this for n successive ratio, so you have to modify. So for this, we use this equation. Say our logarithmic decrement or ratio of log of the n successive ratio amplitude is x naught by n, which is equal to n times of logarithmic decrement. And if you put this delta value is 2 pi d, we get 1 by d is equal to 1 by 2 pi n ln x naught by xn, where n is the number from successive number of this ratio. So by this equation, we easily get the damping ratio, by which method is called logarithmic decrement method. So it is very very important. There's a two methods is I am discussing here. One is a half bandwidth method, which is d is equal to where d is equal to f2 minus f1 divided 2 f8. Another formula is logarithmic decrement method, where delta is represented as logarithmic decrement, which is equal to ln into x1 by x2, which is further equal to 2 pi d, from where we get the damping ratio d. For n successive, this damping ratio uh, is equal to 1 by 2 pi n ln x naught by xn. Now, here is some test. Also, we can find out this coefficient of compression. So, for concentration test, settlement versus displacement load, we find out increment load versus increment displacement. If you plot this graph is look like this on a linear graph. And if you the slope of this linear graph is nothing but called the coefficient of uniform compression, and it is represented as P by delta. So by this equation we directly, or by this test we directly find out this coefficient of uniform compression. Now there is another test which is called hammer test. By hammer test we easily find out the elastic modulus of the system, also shear modulus of the system. So these are the formula to find out the elastic modulus of the system. You remember this? Now moving to the lecture number 58, which is also belong to some questionnaires. And now we try to solve this question one by one, which is very simple questions. So I think the first question I am also covered. So we already actually this is repetitive on already in lecture number 56. But in lecture number 56, we for last concept we need this logarithmic decrement concept. I think it is now clear to everyone. So I am skip this one. And then moving to the next question, which is very simple. So here we need the concept of P by delta, which is equal to the coefficient of uniform compression, elastic coefficient of elastic uniform compression. So, so it is given that a cyclic plate load test of an plate size given 0.6 meter by 0.6 meter settles 0.65 mm under a pressure of 20 kN per meter square. On unloading, observe the plate settlement is zero point 0.6 uh, mm. So determine the coefficient of elastic uniform compression of the soil. So by unloading and loading test, we get the increment settlement, which is equal to the for loading it is 0.65, for unloading it is zero point 0.6. So the increment settlement is 0.05 mm, and our pressure is P is 20 kilonewton per meter square. So if you put CU is equal to P by delta, or it is a delta, then it is 20 by 0.05 mm, but it is in kilometer per meter square, so you have to convert it in meter 10 to the minus 3. So it is become 20 divided by 0.05 divided by 1000, sorry, into 1000, which is equal to 4 lakh, uh, 4 1 2 3 4 5. So 4 lakh kilonewton per meter cube. So our answer is 4 lakh kilonewton per meter cube. We further calculate the value of K, but in question it is not given to find out this. So K, we know that Cu into A, area of the foundation. So Cu here 4000, sorry 4 lakh, and area of the foundation is zero point 0.6 square. So answer is 1 lakh 44,000 kilonewton per meter. So our stiffness of the system is 1 lakh 44,000 kilonewton per meter. Now I think it is understand to everyone. It is very simple question. So I think it is understand. Now moving to the next question, which is said that a mass attached a spring of 5 Newton per mm. So spring coefficient is given 5 Newton per mm, has a viscous damping device. When the mass is displaced and released, the periodic vibration was found to be 2 seconds. So T is given, time period is given 2 seconds. The ratio of consecutive amplitude is given 10 by 3. That means uh, logarithmic decrement is given. Determine the damping factor and natural frequency of the system. It is very simple. And also determine the amplitude motion when force is amplitude of the motion and force of system is given 3 sine 40 and acts on the system. So we have to find out the motion force amplitude and amplitude of this system, and this is I think related to the constant force system for damped force vibration. So first we have to find out the damping factor, then natural frequency of the system. So we know that K is given, which is 5 Newton per mm. You have to convert it in Newton per meter. So it is given 5000 Newton per meter. Then natural frequency, you have to find out for first phi t is equal to 2 second. We know that t is equal to 2 pi by omega. So omega is equal to 2 pi by t. T is here 2 second, 2 pi by 2, which is equal to pi. We know that pi is equal to 3.14 radian per second. We have to find out the natural frequency. Now we have to find out the damping factor, that means damping ratio. So for finding out the damping ratio, for finding out, we use logarithmic decrement equation. So ln, this ratio is given 10 by 3, which is equal to 2 pi d. So d is equal to 1 pi, d is equal to 1 by 2 pi ln 10 by 3. So ln 10 divided by 3 divided by 2 divided by 3.14, which is equal to 0.191, and if you in percentage it is 19.17 percentage. So our D is 19.17 percentage. Now after that we find first this one. Now we have to find out the amplitude motion amplitude of the motion. So we know that U is equal to F naught by K root over 1 minus omega by omega n square whole square plus 2d omega n whole square. So in question, the force is given, F is given 3 sine 40. So if you write this is in form, that is F is equal to F naught sine omega t, then our F naught is 3 and omega is 4 radian per second, which is Newton. Put all this value, F naught here 3, K is 5000 root over 1 minus omega value is here 4, and natural frequency omega is 3.14 whole square, again whole square, plus 2d value is 0.1917, and omega is 4 and natural frequency 1.1 whole square. So put all this value here and get the answer. So 3 divided by 5000 root over 1 minus 4 divided by 3.14 whole square plus 2 into 0.1917 and 2 into 0.1917 into 3, sorry, into 4 divided by 3.14 whole square. The answer is 7.58 into 10 to the power minus 4 in meter. If you convert it in mm, which is equal to 0.758 mm. So our answer is 0.758 mm. I think it is understand to everyone. It is very difficult formula. You have to remember all this formula to solve this question. First, you have to remember t is equal to 2 pi by omega. Then we have to remember the logarithm decrement delta is equal to ln into ratio of this amplitude u1 by u2 successive amplitude, which is further to 2 pi d. If we arrange this, which is d is equal to 1 by 2 pi into ln into ratio of this amplitude. After that, you find out the d and omega. After that, for forcing frequency, for forcing constant for vibration, the amplitude formula or equation is f naught by k divided over 1 minus omega by omega n whole square whole omega n omega square by omega n square whole square minus 2d omega by omega n whole square. So so for this we have to find out for f naught and omega. So it is given in equation f naught is 3 and omega is 4 by this force 3 sine omega 4t. Put all this value and it is coming. You have to make sure the units are in Newton and meter, and this answer is come first in meter. You have to convert in mm, which is and given that 0.758 mm. Now moving to the next question. This is, I think, for this we have to need one graph sheet and plot the data and find out the value. Then it is said that plot the frequency versus amplitude response curve. So first you have to plot this frequency versus amplitude curve, then determine the stiffness and damping ratio of the foundation soil system for the following data. So here it is plotted here. So from this curve, uh, after plotting this is in terms of micron, so 10 to the power 6 meter, 10 to the power minus 6, I think, and in mm. So in meter, it is an mm. So in meter, it is 10 to the power minus 9 meter, and this is in CPM. So for convert to CPS, you have to divide 1 by 60. Okay. And weight of the foundation is given 8 kilonewton, and eccentric moment is given 0.56 Newton meter, and determine the coefficient of uniform compression and damping as per the IS 5249. So for this, one data is missing, which is the size of the footing is 1.4 meter by 4 meter. So you have to use to find out the uh, the stiffness of the system. So let's start with the problem. So first, we know that 'that yes. First, we know that it half bandwidth system, the maximum amplitude is 90. So at 1 by root 2 of this 90, which is equal to 63. So I think here. So one frequency is 5 1580. Another one is at adjustment 1740. So all convert all this in CPM. So at maximum amplitude is 63, uh, 1 by root 2 of 63.63. So our F1 is 13, sorry, 1540, sorry, 1580, converted in CPS, which is divided by, wait. I think network is disconnected. Is right. I'm again sharing. Please wait. So again back to this lecture. So first we find out F1. F1 is in CPS is 1580 divided by 60, which is equal to 26 point, sorry, it is 1 26.8, so 26.33 CPS. And F1, or I think we don't need this conversion, directly use this. So F1 we find out from this graph is 1580. F2 we have to we find out from this graph is 1740, or Fn we from this graph it is 1650. So put all this value in this half bed with the equation, which is nothing but F, so D is equal to F2 minus F1 divided by 2 Fn. So put F1 is F2 is 1740. F2 is F1 is 1580. Then Fn is 1650 into 2. So it is 1740 minus 1580 divided by 1650 divided by 2, which is equal to 0.05. So which is almost equal to zero point zero 0.05. So we say 5%. So our damping ratio is ratio is 5%. Then in question it is said that we have to find out the stiffness of the system. So first, for this, we know that Cu is equal to or K is equal to, first find out the uh, coefficient of uniform compression. 4 pi square Fn square into m divided by A. So stiffness is not required A. So K first find out 4 pi square Fn square into m. So Fn is in, we have to find out Fn in CPS. So 61650 divided by 60, which is become 27.5 CPS. So put all this below. M is given 8 kilonewton. So we have to divide it by 9.81. So 4 pi square into 27.5 square into M is 8 by 9.81. So our answer is stiffness is 4 into 3.14 square into 27.5 square into 8 divided by 9.81, which is equal to, in kilonewton, it is given in kilonewton, so you have to put answer also in kilonewton. So double 2.35 kilometer per meter. So now to solve for I score formula, we have to solve this again. So we know that the maximum frequency or maximum amplitude of any system, resonant amplitude. Now this equation, this problem we have to solve in I square formula. So we know that U maximum at resonant frequency is equal to for rotating mass m e naught divided by m divided by root over d by root over 1 minus d square. So if you simplify this, because we know this damping is much more less, so this become m e into e divided by m into 1 by 2d. And in the graph, we find out that this maximum is 90 into 10 to the power minus 9 meter. So put all this value here, 90 into 10 to the power 9. So we get ME, this moment is given here 0.15 Newton meter. So it's given 0.156, I think, 0.156 Newton meter, and M is given 8 kilonewton. So we have to convert it in Newton divided by 9.81. So put all this value, we get the D. So if you write D is equal to, in simpler way, ME E divided by M into 1 by 2 U max. So put all this value. ME is given 0.156. ME divided by 8000 divided by 8000 divided by 9.81 into 9.81 into 10 to the power 9 divided by 2. So answer is, sorry, 90, 19 to 9. I think. Sorry, this is not 1 to the power 6, it is minus 10 to the minus 6, not 10 to the minus 9. Like I am wrong here, so just adjust here. So I am putting this value 0.156 into divided by 8000 into 9.81 or into 1 by 2 into 90 in divided by 6. So answer is 0.156. So I'm mistaken. It is W. So so no need to divided by 9.81. We have to remove 9.81 because here we multiply G. Here we also multiply G. So it will become W. It is also become WE. So answer is 0.156 divided by 8,000 into 2 into 90 into 10 to the power 6, which is equal to 0.1083, almost equal to 10.83%. So you see that by half band width method, the damping is we find out almost equal to 5%. But at a maximum amplitude method, this damping we find out 10.83%. And I think half band width is more reliable because it use the average of the total amplitude. So it is give the average damping ratio of the system, but this maximum amplitude give only the damping ratio corresponding to the maximum value. So I think it is I have to neglect. Now for finding out, I think it is now this problem is now completed. We already find out this. Now we have to find out this coefficient of uniform compression. So coefficient of uniform compression Cu is equal to 4 pi square Fn square m divided by A, where A is given 0.4 by 4 meters. So 4 pi square Fn square, Fn is point 1 sorry 27.5 whole square, m is 8 divided by 9.81, and this is A is point 4 square. So answer is 4 into 0.13, 4 into 3.14 square into 27.5 square into 8, uh, divided by 9.81, 0.4 square, which is equal to 52014.72 kilonewton per meter cube. I think this problem is completed and we already completed this lecture number 15. So now moving to the lecture number 58 or 59. So which is regarding to the different types of foundation and what are the different use of this foundation. So I think it is already 16 or 17. We come exceeding the time. So we have now have to stop here. This lecture number 59 and 60, also the previous lectures we discuss in tomorrow extra session, which is on 14th April, uh, and that is tomorrow, and timing will be same. So now I stop here. So we will meet again in the tomorrow's class, which is our last class of this session. So we don't. I think it is tomorrow's session. It is the recap all of all the all the classes we just briefly discuss these lectures again, and we also complete some numerical problem of the pile group foundation, sheet pile, and anchor pile. So be with us, and then we solve it and conclude our session tomorrow. So now we have to do one thing. You do the revision of the previous classes. Also try to solve the questions by yourself, because exam is in just in 2 weeks. So please prepare by yourself and continue reading these lectures. All the things are given in these lectures. It is very simple topic. So please try yourself. Try by yourself. So now I stop here. So thank you everyone. Good night. We meet in the next class, that is tomorrow. So thank you.